This lecture is given to the Gabor-Zegert Prize winner, Atul Dixit, and the citation is that the 2021 Gabor-Zegert Prize is awarded to Atul Dixit for his impressive scientific work solving problems related to number theory using special functions, in particular related to the work of Ramanujan. Atul is an associate professor of mathematics at the Indian Institute of Technology, Gandhihar. He did his bachelor's in computer engineering at the University of Mumbai, India, and then a master's in mathematics at Texas Tech University, followed by a PhD at the University of Illinois at Urbana, Japan. He did his postdoc at Tulane before moving to the Indian Institute of Technology, Gandhihar, as an assistant professor. So, Atul, we look forward to your talk, Lambert series.
Good morning, everyone. Thank you very much, Professor Clarkson, for the kind introduction. I would like to thank everyone in the Gabor-Zegert Prize Committee for giving this award to me. I know it comes with a big responsibility, and I'll strive to live up to the expectations put forth by the committee as well as by my well-wishers. So today I will be talking on this topic of generalized Lambert series, which is something I have worked on for the past several years. So this is based on joint work with my postdocs and PhD students. So Vivekananda Maji and Soumyarup Banerjee as postdocs, and Rahul, Rajat, Ashita, and Shivajee as my PhD students. So let me begin and continue with the tradition of what Hjalmar started in his talk. So that is to start with a photograph. Professor Askey. So this is during his 80th birthday celebration at Wisconsin. And as we all have seen in Hjalmar's talk also, this is the same photo. I mean, he's wearing the same coat and the shirt that was there in the OPSFA web page that is there. Okay, so I'll begin with modular forms. What is a modular form? A modular form of weight k on SL2Z is a function defined on the upper half plane H with following properties. So f is holomorphic on H. F is also holomorphic at infinity, which is perceived in the positive imaginary direction. And F satisfies this beautiful symmetry. F evaluated at AZ plus B over CZ plus D equal to F itself, except for this factor of automorphy in front, that is CZ plus D to the power K. And this is for any Z in the upper half plane and for all ABCD matrices in SL2Z. A typical example of a modular form is the Eisenstein series of weight k, where k is an even positive integer greater than 2, and it is defined in this way. So here zeta is the Riemann zeta function, and this is a series, the Fourier series corresponding to this function, which I'll define on the next slide. Considering a more general series where a is any complex number and real part of y is greater than 0. So here sigma sub a of n is nothing but the sum of 8 powers of all divisors of n. And it is a very simple calculation to write this in this particular form. So when I take a to be a, say, 2m plus 1, positive odd integer, and let me take y to be minus 2 pi I z. So real part of y greater than 0 corresponds to z being in the upper half plane if we make this change of variable. So then what is this particular series? It is nothing but essentially the Eisenstein series of weight 2m plus 2, except for this normalization factor involving the Riemann zeta function in front and plus 1. Happens if we take a to be a negative integer, then this particular series represents what is known as a Eichler integral corresponding to the Eisenstein series E2m plus 2 of z. So if you have Eisenstein series Ek of z, then an Eichler integral corresponding to that Eisenstein series is the kth antiderivative of that Eisenstein series. If I take a to be equal to 1, then this is essentially the quasi-modular form E2. And if I take a to be minus 1, then this is the series which appears in the transformation formula for the log of Dedekind eta function. So we know that Dedekind eta function is a half integral weight modular form. So eta of minus 1 over z is square root of minus iz times eta of z. So if you take log on both sides and then simplify a bit, then this is the series that we will encounter. Okay, this particular series is a special case of what is known in general as a Lambert series. A Lambert series is defined as summation a of n q to the n over 1 minus q to the n, where a of n is an arithmetic function and q is a complex number inside the unit disk. if I take Q to be equal to e to the minus y, then one can write this series, the Lambert series, in this particular form. And so the previous example was with a of n being n to the power a. And of course, one can also write this as a double series. And if we do that, then the coefficients that we get are nothing but the Dirichlet convolution defined in this particular way of a, the arithmetic function a, with a function which is identically equal to 1 at all natural numbers. Okay, so we will be making use of this again and again. Let me now look at a formula of Ramanujan for all zeta values. So let alpha and beta be positive real numbers. Actually, this also holds when you have alpha and beta in the right half plane, such that their product is equal to pi square. Then for any non-zero integer m, you have this beautiful symmetric relation. So on the left-hand side, you have a formula, you have an expression involving alpha. It involves the odd zeta value, zeta 2m plus 1, and the Lambert series corresponding to a of n being n to the minus 2m minus 1. Or in other words, if we take the exponent as a, we are putting a to be minus 2m minus 1. And the same thing is transformed into something which looks like it, except for a factor of minus 1 to the minus m, or minus 1 to the m in front, and alpha replaced by beta. There's also a finite sum involving Bernoulli numbers, which is kind of causing an obstruction to modularity, as one may say. Now, I will talk about why this formula is important, but before that, I would like to say that a special case of this formula was given by Lerch in 1903, and that is corresponding to when alpha equal to beta equal to pi, and m is odd. So note that if m is odd, minus 1 to the minus m will give a minus sign in front, and alpha beta are the same. So this thing will be minus of this particular thing. So if you take that on the left-hand side, we have just one odd zeta value, we have just one Lambert series, and their sum is equal to this finite sum involving Bernoulli numbers. So the history, implications, and modern interpretations of this formula are given in a nice survey article by Bruce Berendt and Armin Stroud. Why is this formula important? Now let me take m to be any negative integer less than minus 1, so that this particular sum vanishes. Say, for example, m is equal to minus 2. Then what we get? N cube over e to the power 2n alpha minus 1. And here also n cube. And this thing is 0. So essentially what this is equivalent to is the transformation formula for the Eisenstein series E4 of Z, the Eisenstein series of weight 4. If you take m equal to minus 2, then this will be corresponding to, minus 3, then this will be corresponding to transformation formula for Eisenstein series of weight 6. So these are modular transformations. What if you put m equal to minus 1? There is the k equal to 0 term that we get, and that destroys modularity. And what do we have here? We have n to the power 1. And so that is nothing but the quasi-modular transformation for the Eisenstein series of weight 2. Not only that, if we take m to be any positive integer, then of course this sum is there. And what we are getting is the transformation formula corresponding to the Eichler integral associated with Eisenstein series of weight 2m plus 2. If we take m to be equal to 0, say here we have a problem because the zeta function has a pole at 1. However, the series itself makes sense. So if we start from the series with m equal to 0 and then represent it as an inverse Snelling transform, and then from there use residue calculus, then we will get to the transformation formula for the log of Dedekind eta function. And we'll get to the fact that the eta function is a half integral weight modular form, the inversion property. I just want to make sure, make clear in the beginning that here alpha going to beta is equivalent to going to minus 1 by z. If we work with the upper half plane, then it is the inversion property in a modular transformation where z goes to minus 1 over z. And that can be equivalently phrased in the form alpha going into some constant over alpha, or in other words, alpha going into beta. So what have we seen? We have seen that this transformation of Ramanujan is encoding a lot of things. It is encoding the transformation properties of Eisenstein series of level 1, that means Eisenstein series on the full modular group, SL2Z, as well as their Eichler integrals. And it is also giving us the transformation formula for the log of Dedekind eta function, all at once. This formula and its corollaries have been used in theoretical computer science. There is a paper by Kirschenhofer and Prodinger on spatial data structures called tries. So they use Ramanujan's identities to achieve certain distribution results on random variables related to these tries. Let me actually come back to this special case due to Lambert, where alpha beta was equal to pi and m is odd. Then this is the formula that we have. Suppose we did not have this particular series. It would be a mind-blowing result, because what it would imply is that any odd zeta value is a rational multiple of pi to the 2m plus 1. And that would imply at once all odd zeta values are transcendental. But that's not really what we are getting, because even though this is a rapidly convergent series, it is there. So at the max, what we can say is at least one of these two is transcendental. That's what we can get from this result of Lambert. The arithmetic nature of odd zeta values is quite mysterious. Up to now, we have been able to only show that zeta of 3 is irrational. That's due to Aperi. And we don't even know whether zeta of 3 is transcendental. Forget about zeta 5, zeta 7. There are no results, except the best result in this direction is due to Zudilin, which says that at least one among zeta of 5, zeta of 7, zeta of 9, or zeta of 11 is irrational. But there is this folklore conjecture which says that if you take any non-zero polynomial in n plus 1 variables, x0, x1, so on up to xn, and you put pi for x0, zeta of 3 for x1, so on up to zeta of 2n plus 1 for xn, then this polynomial will never be equal to 0. See, n is any natural number. So if I take in particular just one variable, say x0, and if I put pi in there, then what does this mean? This tells me that pi is transcendental. That is already known. But I can also put, instead of x0, instead of pi, I can only put, I can put zeta of 3. And that will imply that zeta of 3 does not satisfy a polynomial equation with rational coefficients. So that implies that zeta of 3 is transcendental. Zeta of 5 is transcendental, and so on. So an easy consequence of this conjecture is that all zeta values, odd zeta values, are transcendental. There is more that we can get. We see that these odd zeta values are not algebraically related to each other. Now, this is starkly different from what we have with even zeta values. There is this famous result of Euler, which says that any even zeta value, zeta evaluated at even integer 2m, is a rational multiple of pi to the power 2m. And so, because pi is transcendental, all even zeta values are transcendental. And not only that, they are algebraically related to each other. Why? Because see, zeta of 4 is pi raised to 4 by 90. Zeta of 2 is pi squared by 6. So we have this relation. Similarly, we have any even zeta value is related to other even zeta value. But nothing of that sort is true in the odd zeta values case. Bruce Bernd in 70s obtained a transformation for a very general Eisenstein series, which gives as corollaries both Euler's formula for zeta of 2m as well as Ramanujan's formula for zeta of 2n plus 1. So they are in some sort companions of each other. Also be focusing on generalized Lambert series, which is something where you put a capital N, any natural number n, the exponent of small n, which is inside this exponential function. And this arithmetic function a can also be dependent on capital N. So on page 332 of the Lost Notebook, at the end, Ramanujan considers this particular series with this arithmetic function being n to the power k. But there is no right-hand side. So we don't know whether there are pages that went missing. We can only speculate about that. But he did consider on the same page a special case when k is equal to 0 and capital N is equal to 2. Now, there are further results by Wigert and also in the early 2000s by Kanemitsu, Tanigawa, and Yoshimoto. But Kanemitsu, Tanigawa, and Yoshimoto have always considered n to be even. And hence, we tried to work with n odd, capital N odd, and we found out that that is a more interesting case. So when capital N is equal to 1, whatever results we have, those should come as special cases of the general odd n, right? So we tried to do this with Ramanujan's formula for odd zeta values, and here is the generalization that we were able to get. So capital N is an odd positive integer. Again, alpha beta can be taken to be in the right half plane as well. But now the condition alpha beta equal to pi square is replaced by alpha beta to the power capital N is pi to the power capital N plus 1. For any non-zero integer m, you have this transformation, which looks frightening at the beginning, but let me explain. As before, there is the side involving alpha, you have alpha to some power, you have an odd zeta value, but instead of zeta 2m plus 1, now you have zeta 2nm plus 1. You have this generalized Lambert series. So with capital N in here, as I showed before, a of n being this arithmetic function. On the right-hand side, you don't have just one generalized Lambert series. You have n of them. So the beta side consists of n generalized Lambert series, and that can be seen from the exponent here. The alpha side has exponent 1, so you have only one Lambert series in here. And then there is again a finite sum involving Bernoulli numbers. Easy to see that if we put capital N is equal to 1, then alpha beta is pi square. Capital N equal to 1 gives you j equal to 0 only. So all of this reduces to just single Lambert series. And this part also becomes 1. And when capital N is 1, n to the power 1 over n, and n to the power n is the same, n. So you get back Ramanujan's result readily. Okay, the nice thing about this is that now you are able to relate two different odd zeta values. In Ramanujan's transformation, you had zeta of 2m plus 1 on the right and zeta of 2m plus 1 on the left, when n is 1. Now you can relate two different odd zeta values with the help of these generalized Lambert series. Himitsu, Tanikawa, and Yoshimoto also considered a more general Lambert series where they put a parameter a satisfying this condition. This is the same parameter that is there in Hurwitz's zeta function. And indeed, if you look at the inverse Mellin transform of this, instead of Riemann's zeta function that consists of Hurwitz's zeta function, zeta of s comma a. A is 1, this reduces to the previous one. So we also were able to get in this work a transformation generalizing Ramanujan with two variables or two parameters, n and a. It links the zeta 2nm plus 1 with this Dirichlet series. Now, note that if a is equal to 1, then we get back zeta 2m plus 1, which was there on the previous page. Okay, I won't go into the complete result in here, but there is an interesting intermediate theorem that we needed, and that is summation of this integral. This integral is sometimes called as Rabel's cosine transform. So this summation of this improper integral is explicitly can be explicitly written in terms of digamma function, gamma prime over gamma. So a moment's look will tell us that one cannot interchange the order of summation and integration. Actually, I'll come towards the end of my talk with this formula again, and I'll say what true thing do we have if you want summation first and integration later. But okay, let me come back to this general series, summation sigma sub a of n e to the minus ny, where a is any complex number. So for a odd, we have seen that this series is instrumental in the theory of modular forms. The case a even is conspicuously absent, except for a equal to 0. There are no results related to that. And that's where we thought of working with this general one and try to get all at once, all results from one single transformation. So there are some results in the literature where, for example, Guinan, he considered a equal to 2k, where k is real, and such that k plus half is not an integer. If k plus half is an integer, then 2k would be an odd integer. So that is the case that is already known. So that's why he takes k plus half to not be an integer. What he does is he writes this in terms of an equivalent series where the exponential now has, instead of y, some constant over y, as is there in modular transformations. But now it's no longer modular. So the modularity is obstructed by means of certain extra integral, which may be a line integral or it may be a principal value integral. So I would like to mention here two approaches that are there. The first approach is what Guinan has done. So you try to see how much you can try to mimic modularity, but then you won't have modularity as such. So you will have some extra term, which is going to remain. It may be a line integral, it may be a principal value integral. Another approach, and which is what we adopted, is that we want a transformation which takes y to some constant over y without having an extra line integral or an extra principal value integral there. We just want this to transform into another series which will have not necessarily this e to the minus ny, but rather some other function, but where y will go into some constant over y. So this is the approach that we have taken. And here is the example of the former approach, similar to Guinan. This is on page 269 of Ramanujan's second notebook. So Ramanujan considers n to be complex, and he takes any complex n with real part greater than 2, then here is what he gets. So now again, this is the Lambert series we have been looking at with the alpha, with beta. There is a transformation, but now n is complex. So there is this appearance of this principal value integral in here. And if you take n to be an even positive integer, this thing becomes 0. So this term is gone. And what you get is the transformation for Eisenstein series. As is the work done by Bettin Conray and many others, they have transformations using the former approach, whereas what we are going to see next is for the latter approach. And that is given in this recent result of mine with Kesarvani and Kumar. This just got accepted last month in research in the mathematical sciences. So you have this series for any complex A with real part of A greater than -1. That series gets transformed into, again, a series which has sigmas of A of n, but now you don't get back exponential function in general. You have something involving the hypergeometric function 1f2 and hyperbolic function. There are a bunch of residual terms as well. Okay, so of course, to this audience, there is no need to give this definition. So here is the definition of the generalized hypergeometric series anyway. So A sub n is the shifted factor. Okay, we have seen the previous formula, which was for real part of A greater than -1. That can be analytically continued in a more general region, or a more general region, which is real part of A greater than -2m -3, where m is any non-negative integer. So see, the left-hand side remains as it is, as it was before. What happens is on the right-hand side. And let me explain this in the next slide. For now, assume that this particular function, along with this thing in the front, is nothing but all that goes in here and in the front. So what happens is that this, and this is a standard trick. How do you analytically continue the previous identity? So you take this particular function, find its asymptotic expansion or an asymptotic formula for it as n tends to infinity, and you add and subtract a requisite number of terms from its asymptotic expansion. The first, say in here, I'm taking first m plus 1 terms from its asymptotic expansion. You subtract those and you also add that, and then evaluate with the help of that series, which gives you this product of zeta, because the Dirichlet series corresponding to sigma A of n is zeta times zeta. I'm assuming real part of A greater than -1. But now we note that because of this subtraction, gained power of n in the denominator. So this particular series is convergent not only now for real part of A greater than -1, but for real part of A greater than -2m -3. In fact, it's uniformly convergent. All of the stuff inside is analytic. All of the things in here are analytic. And so by means of analytic continuation, we can show that the whole identity is valid in this expanded region. See, one may say that, okay, what happens when A is equal to -2k -1? There is a pole of the zeta function. But fortunately, there is also a pole of the gamma function when A is -2k -1. So things work out. Okay, so this is something that we call as master identity. So I'll come back to it, why we call it as a master identity. But let me first define this particular function. It's a generalization of the modified Bessel function of the second kind, which is for this particular parameters defined as essentially a difference of 1f2 functions. In modified Bessel function of the second kind, we have difference of 0f1s. Here it is 1f2s. So when w equal to 0, this was considered by Koshlyakov, and it's there in one of his papers from 1938. But one can also get a more general one with a w put in there. And when mu equal to -nu reduces to the modified Bessel function. Okay, let me come back to the master identity. Or no, not master identity. I have just looked at this transformation, the earlier one. Okay, why is this important, or why is the master identity important? Because you can put here A to be an odd integer, and you will get Ramanujan's formula as a special case. But you can also put A to be an even integer. I mean, not here, I want even integer as in even positive integer or even negative integer. So we will have to take the version of this, which is by analytic continuation. In fact, this. You can put A to be even integer, and that too gives us nice transformations. They are no longer modular. but there are transformations which exist and they are very natural, as I'll try to demonstrate. Okay, so this is the transformation that we get for A equal to 2m, where m is a natural number. What is this Lambert series getting transformed into? It is transformed into something which looks something which has two new functions. These are actually well-known special functions. They are hyperbolic cosine and sine integrals. They are defined in this particular. But why does this particular combination appear is what I'll try to explain. Let us look at this particular series with A being an even integer. As I said on the previous slide, we get this particular series. This transforms into this particular series. Let us take a special case where m is a non-positive integer. So then this thing vanishes and you have just this part. So when A is equal to 2m, what do we get when A is equal to 2m plus 1? Well, when we have here 2m plus 1, this particular series transforms into itself with y getting replaced by some constant over y. That is this particular one. But that exponential function is nothing but a difference of this hyperbolic functions. What is the difference between odd and even case is that with odd A, you get just difference of hyperbolic functions. With even A, you get not just hyperbolic functions in here, but the hyperbolic sine and cosine integrals also come out. So that's the difference between A even and A odd. So this is, it can be done for any integer. That's what I wanted to say. So for example, when we did it for A equal to minus 2m, the previous one was A equal to plus 2m. Now here we do it for A equal to minus 2m. And note that this is a companion to Ramanujan's formula, because in Ramanujan's formula, there was zeta 2m plus 1, there was n to the minus 2m minus. What is this Lambert series getting transformed into? It's no longer a Lambert series again. This is some combination of digamma functions that we get. But on the right-hand side, the finite sum, which initially involved just the Bernoulli numbers, as in Ramanujan's formula, and a Bernoulli number with even index is nothing but even zeta value. So in Ramanujan's formula, there were only two even zeta values. Now here, you have a combination of an even zeta value and an odd zeta value. That's the difference. When we found this formula, and then when we looked at the literature, there was one result due to David Bradley, where he was considering G to be a periodic function of period Q, and he considered the Dirichlet series, and he found out a transformation. Now, if you look here, then our first reaction was that, okay, he already has our result. But then we found out that here it says G is odd. So G cannot be identically equal to 1, which is what we had in our previous formula. And also, it cannot be true that this gives us our formula, because on the right-hand side, there is again a Lambert series, whereas we had a combination of digamma functions. But he also has it for G even. But when G is even, he has 2m plus 1 in here, as well as minus 2m minus 1. So this is actually a generalization of Ramanujan's formula, but it doesn't give that companion that I showed you before. So there are similar results due to Bernd as well as by Katayama. Okay, there is another result corresponding to A equal to 0. So if I take n to the power A as my arithmetic function and A is equal to 0, then that was known previously due to Wigert from this paper. This formula has not received much attention. Actually, it's very useful. Why is it useful? Note that in all of these formulas, even with general complex A, what have we seen in all these transformations? On the left-hand side, there is exponential ny minus 1. On the right-hand side, everywhere you have 1 over y. So if I want to get, for example, the asymptotic expansion of this particular series as y tends to 0, just look at the right-hand side. You have asymptotic expansion, well-known asymptotic expansions for digamma function. And from here, you can get this result, which is there in Titchmarsh's book. And it is proved starting from the left-hand side and using contour integration and Mellin transforms. But it comes just as a ready consequence of this particular transformation due to Wigert, which is not only true for y tending to 0, but for any real y greater than 0. So much more. But anyway, this asymptotic formula is quite useful in the theory of the Riemann zeta function. So let me first talk about where it comes into use. So people in analytic number theory study very much these moments of the Riemann zeta function on the critical line. So this is the 2kth moment of the Riemann zeta function on the critical line. There are conjectured asymptotics for this as t tends to infinity. T tending to infinity, this is what is believed to be true. It is asymptotic to ck times t log t to the power k square. However, this has been established only for k equal to 1 and k equal to 2 so far. And k equal to 1 was done by Hardy and Littlewood in 1918, and k equal to 2 was done by Ingham in 1930s, somewhere around 1934. And from there up to now, nothing is known for higher values of k. Whether there are many evidences that this is correct, coming from random matrix theory, from physics. There are many models also which give evidence to this fact that this must be true. However, there is no rigorous proof up to now. People sometimes also study this smoothly weighted moment. So if you look at the previous one, here we have to put a finite number t. If t is infinity, then this integral diverges. And that's why, this is the asymptotic that we have. But if you put an exponential dampening factor in here, e to the minus delta t, say delta is positive, then we can extend it up to infinity. And people actually study such moments also, smoothly weighted moments. Now, why are these important as well? Because if you know asymptotic for this, you can easily get asymptotic for this, and vice versa. And that is much more, true, much more in general, whenever you have a function which is non-negative. That is, in here you have absolute value of zeta function on the critical line. So whenever you have non-negative function f, you can get a correspondence between asymptotic for the smoothly weighted moment, or f of t times e to the minus delta t, and the previous integral. So that's why study of this is also quite important. So now, using this asymptotic that I showed you on 2 slides back, so let me go here, this one. Using this asymptotic, where d of n is the divisor function, F.V. Atkinson gave a simple proof of a result of Kober, which was the asymptotic estimate. So this smoothly weighted moment is having in here this behavior as delta tends to 0. This is these constants Cn are effectively computable. In the remaining part of my talk, I will be mentioning our recent work. Just a few days back, end of May, we submitted this paper. What we did here is that we were able to get an exact transformation for the Lambert series corresponding to log n, a of n equal to log n. Such a result was not there in the literature before. And at the end, I'll say why it possibly would have been missed. We have a transformation which takes y to 1 over y. Note this equality, which we saw at the beginning of the lecture. This particular series can be written in this particular form where you have this Dirichlet convolution. So if I put a of n to be equal to log n, then here I have 1 star log of n. Definition, that is summation d dividing n log d. Summation d dividing n log d. Log is additive function, so that gives me log of product over all divisors d of n. And product of all divisors d of n is nothing but n to the power d of n over 2. That's a fact coming from elementary number theory. And so if I put this in here, what I get is that the Lambert series for logarithm is equal to this particular series. So the one that we have seen before is with d of n e raised to minus ny. Now it is d of n log n e raised to minus ny. And there is an explicit transformation that is there in here. What does that explicit transformation look like? Well, before we see that, we need to look at what this Denninger function is. So in 1984, Christopher Denninger wrote a very influential paper where he studied a function r, which for now I will define on the positive real line itself, is uniquely defined by this difference equation. R of x plus 1 minus r of x is log square x with this initial condition. Now let us see, what if we have log x? Can we think of a simple solution to this difference equation with log x instead of log square x? Well, that is log gamma of x. Forget about this initial condition, but it's log gamma of x plus 1 minus log gamma of x, which is nothing but log gamma x plus 1 over gamma of x, which is log x. So what is this R function? This is a higher analog of log of gamma function. So this is what Denninger looked at. He also showed that R of x can be analytically continued in the entire complex plane except for negative real numbers and 0. If this corresponds to log of gamma, then what will be exponential of R of x? That will be some higher analog of gamma function, right? So it is known as Ramanujan-Denninger gamma function because Ramanujan worked on its logarithmic derivative. So this is the logarithmic derivative. Here gamma 1 is the first Stieltjes constant. So compare this with the series definition of the digamma function. One has minus gamma, the Euler's constant. One has 1 in here, 1 in here, and 1 in here. So when one goes to the higher analogues of digamma function, this first one involves the first Stieltjes constant, but more general one has been studied by Carl Dilcher, and that is psi sub k of z. And there you have minus gamma sub k, the kth Stieltjes constant. One has log z to the power k, log n plus z to the power k, and log n to the power k. He has also studied the gamma functions corresponding to these in their theory. So it's a beautiful paper. And the case when k was 2 was considered by Denninger in his work. Okay, so now we are ready to see what that transformation looks like. So this particular Lambert series of log can be transformed into this one. There are a bunch of residual terms again, but everywhere on the right-hand side, you can see y going into 1 over y. So on this side, you had y. On the other side, you have everywhere 1 over y. I mean, log square y is same as log square 1 over y. Log y is same as minus log of 1 over y. In this series, everywhere you see y in the denominator. Here is the place where one has y. One has this psi 1, the higher analog of digamma function. So before I go over the proof, I just wanted to say that the starting step towards proving this is the transformation I had discussed in the beginning of my talk. And we'll see this brief ingredients in the proof of this. But the idea is quite simple, but then later on one has to use a lot of new theorems. Because we have seen that y goes to 1 over y on the right-hand side, if I want to look at the complete asymptotic expansion of this left-hand side as y tends to 0, even that was not known. But now, with the help of this right-hand side, one can get the complete asymptotic expansion as y tends to 0 of the left-hand side. And not only is that true, it's true for any y in the right half plane. So that's in here. Anyway, so we'll look at this result where we get this asymptotic expansion, and its straightforward consequence is a Kober type asymptotic expansion for this moment of the Riemann zeta function, where now this thing is no longer real. Initially, what you had was modulus of zeta half plus it square, which is nothing but zeta half plus it, zeta half minus it. Now you have zeta half minus it, but you have zeta dash half plus it. So this is no longer a real quantity. Has there been any result where one gets not a full asymptotic expansion, but a leading order asymptotic term in this particular one, or the corresponding moment where one takes a t in here and one doesn't have this exponential dampening factor? So the answer is yes. It's known due to work of Gunning. For any derivative, I mean, muth derivative of zeta half plus it and nuth derivative of zeta half minus it, the leading order term is known. And Turnage-Butterbaugh has shown, in fact, that this is the main term, this is the error term that you have. In fact, if I put mu equal to 1 and nu equal to 0, then that was the case that I showed you before, but with infinity and the exponential factor in there. So without that, this is giving us minus t over 2 log square t. Come back to this because I want to again point out a very mysterious correspondence that is going on between this integral and this integral. I mean, the asymptotic of this is kind of corresponding to asymptotic of this in the same way as it was happening with mod of zeta half plus it square. So I'll come back to it, but let me first give the complete asymptotic expansion of the left-hand side, the Lambert series of logarithm, as y tends to 0. This is what one, and that comes readily from our main result. And here is the application of the latter asymptotic expansion. This moment behaves like this. Again, these decays are effectively computable constants. So let me see how much time I have. Around 17 minutes. So let us look at just the leading order term. Okay, I mean, it will be minus log square delta over 4 sine delta over 2, right? That is the part which contributes the most towards this as delta tends to 0. Minus log square delta over 4 sine delta over 2. Now, as delta tends to 0, sine delta over 2 is same as delta over 2. So 4 times delta over 2 is just 2 delta. So you have essentially minus log square delta over 2 delta. Now, what if you put delta equal to 1 over t in there, giving this delta which was in the denominator goes in top because delta is 1 over t. So there is a t in top. And then there was log square delta, which is log square 1 over t, which is same as log square t, with a minus sign in front, which is also in here. So why do I say this is mysterious? This is mysterious because this function is no longer non-negative. It's in fact a complex valued function. And a result in Titchmarsh's book that I mentioned previously requires that f be non-negative in order to have this correspondence between the two moments. But we are seeing that something similar is true even though this f, the function, is a complex valued function. This is not given in Titchmarsh's book. I also looked at a paper of Hardy and Littlewood on Tauberian theorems where there are a number of results of this type which are given, but all of them I mean, there is none which requires, none which has f to be a complex valued function. So there is much more that is going at the background that should be investigated. This is what I wanted to say. Okay, let us come back to this transformation and try to prove it. So as I said, the basic starting step is the transformation I looked at previously for any complex A. The idea is simple. You differentiate with respect to A and then let A be equal to 0 or A tend to 0. The left-hand side is very easy to differentiate with respect to A and then let A tend to 0. That gives us the log n over e raised to n minus 1, that series. This one is also an easy limit calculation. After differentiation, you put A tends to 0, calculate the limit. The main thing, however, is to try to see what the right-hand side turns out to be after the differentiation and specializing A. You see, A appears everywhere, right? So how do we do? And it is in this regard that I would just like to say that there were at least 2 magical moments that happened while we were working on this. And had those not occurred, if they would not have occurred, we probably would not have been able to discover this formula. Let me say why it is slightly difficult or a lot more difficult to get a required output from here, the one that would be useful, the one which is natural. Because if you differentiate this with respect to A and put A tend to 0, then you are left with this triple series. This triple series is quite complicated. There are logarithms here. There is a psi of 2k plus 1. There is psi square of 2k plus 1 and psi dash of 2k plus 1, the derivative. Write it in this form. And there are 2 series which involve this digamma function. The first one we had handled in our previous work. In fact, we found out this identity where again these hyperbolic sine and cosine integrals play a natural role. But we knew nothing about this right-hand side. And the first magical moment happened when we were going over a paper of Alexander Appelblatt, a recent paper from 2019 or 2020, not with the intention that we will get something which will be useful for this. We were just going over that, and all of a sudden, out of the blue, we saw something very similar to this particular series. And that was related to what is known as the Mittag-Leffler function. This is the 2-variable Mittag-Leffler function, E a comma b of c. It is defined in this way. It's a very popular function. What was there in Appelblatt's paper was this particular result. Now note that on the previous slide, the series that we encountered was with a equal to 2, b equal to 1, and t taking some value depending on n and y. So we found out there that this was actually accessible through this Mittag-Leffler function when you differentiate it with respect to the parameter b twice. Okay, the next challenge was that no closed form expressions are known for this. There are closed form expressions that are known when you take the first derivative with respect to B or with respect to A. And Appelblatt has a long list of explicit evaluations for this first derivatives with respect to the parameters. But for second derivatives, there is nothing. There is major thing that we needed to do was to really find out an expression for this. Because you see, with A equal to 2 and B equal to 1 is what we require. So it's like you take this with A equal to 2 and then evaluate at B equal to 1. So we were able to get this relation which links this particular series of digamma functions with this particular integral. If you have sine in here instead of cosine, this integral is not difficult. But with cosine, it is quite difficult. I mean, it doesn't have any closed form expression. If you put in Mathematica just gives it back. Okay, again, how did we come across this particular relation? That was the second magical moment. So it so happened that I was looking over MathSciNet on a review of a monograph by Mkhitar Zerbashan. Sorry if I mispronounce this name. Zerbashan was an Armenian mathematician who made fundamental contributions in harmonic analysis, theory of analytic functions. And he is the one who is credited with raising the Armenian mathematical school to high international standards. So I was going over MathSciNet review of his monograph, where it was mentioned in the review that he has one representation for the Mittag-Leffler function, which was exactly what we needed, E2, B. Not with any general A, it was only with A equal to 2 that he had given. So I went into, I found the monograph, and then I looked at that expression and tried to differentiate that, but things were getting very tedious. Then on the next page, we found out that there are two other representations that Zerbashan had given. And the first one out of them was the key. So here is the representation for this Mittag-Leffler function. Note that Zerbashan doesn't have it for any A. He has it only for A equal to 2, and the case was what we needed, the A equal to 2 case. So the previous theorem that I had follows by taking second derivative with respect to B on both sides, and there are a lot of computations that need to be done, and one needs to also use this integral evaluation. That way, we are able to get this representation for this. We take this and we put it in here. Take this right-hand side and we put it in here. And we simplify, and there are magical simplifications that happen. And what we get is this double series of integral, the same integral that we had, right? U cosine U log U over this. That was what we saw in the previous theorem. Okay, so we are here. Now, how do we proceed from here? So before going over that, let me digress a little bit and say that, I'll digress after this slide. So here is this higher analog of digamma function that we had seen before. So the next result that we needed was for this inner sum, the inner sum of integrals, explicit representation in terms of the digamma function and this higher analog of the digamma function. This also requires quite a bit of work. I'll mention two results just in passing that we require in order to do this. But now let us compare this with something that I talked in the beginning of my talk. And that was this summation of integral, this Rabe's cosine transform having this explicit evaluation. Look at the left-hand sides here. The only thing is that there is this extra logarithmic factor. Otherwise, everything is the same. So while this involves the digamma function, this one not only involves digamma function, but its higher analog as well. Okay, now I will digress and then try to see what happens if I naively try to interchange the order of summation and integration. It's divergent integral that I get. But there is something interesting that one gets from here. And that is quite instructive also for a class in the real analysis, let's say. So this summation of integral is equal to this, where you have integral first, then summation, and the exact same thing as you have here, but there is this minus 1 over 4w cosine of u. Of course, one cannot separate out this to, one cannot write this as a difference of integrals. It would be a divergent integral that one gets here. So this last year was accepted as a problem in American Mathematical Monthly. So how I found out this result was kind of indirectly. For this one, in our previous work, we already had this right-hand side. And I noticed that the same right-hand side is given in a paper of Wigert for an integral, which if I manipulate, gives rise to this one. It requires the partial fraction expansion of hyperbolic cotangent. And if you do that, then this is what one gets. The direct proof, as was given by the referee for this problem, was involving quite a bit of things like Lebesgue's dominated convergence theorem, and one has to apply it many times. So there were, but it's an interesting thing. I wonder whether there is an analog of this where you have this logarithmic factor from the previous slide. So this emphasizes the importance of checking the interchange of summation and integration. Okay, I'll just mention this is a these are the two results. We had to develop the asymptotic expansion of this psi1 from scratch. This is what it is. And we also needed this inverse Smelling transform representation of psi1. Okay, in a minute or so, I will stop. So I would like to just say that why was this transformation for Lambert series of logarithm missing from the literature? Because perhaps a transformation for this particular series was not there in the literature. It was only the special cases when a takes value 0 or a is any odd integer that people had studied. But because now here a is a continuous parameter, in fact, a complex number here, we could differentiate, and that led us to this. How does one find that transformation that I have been talking again and again? That involves a lot of special function theory and theory of integral transforms. It involves Voronoi summation formula, as well as integral transforms which involve Bessel functions or combination of Bessel functions in their kernel. So I'm skipping that part. What I want to say is that integral transforms are very much useful in number theory. Also, these higher analogues of digamma function, the psi1 which came in our work and psi k, which has been studied by people like Ishibashi and Dilcher, they are also quite important. They occur in number theory. These applications we have already discussed. Closing, I would like to say one quote by Ishibashi. He says that Denninger proved several analytic properties of R2 of x, that is the same function that R of x, the Denninger function, in order to familiarize and assimilate it as one of the most commonly used number theoretic special functions. And our work is a modest addition to the already growing literature on Denninger's function and its derivative. I mean, there are a number of papers that are coming recently. In December 2021, there was a paper on Ramanujan Denninger gamma function. There is Dilcher's paper and many others due to Ishibashi. So there is a growing literature on this, and ours is a modest addition in there. With that, I will stop. Thank you.
Thank you, Atul. Are there any questions?
Maybe I could give a short comment or a half question, half comment, Atul.
Sure.
Well, regarding these difference equations you have shown of this Danninger or whatever was the name of that function, that r plus x was x plus 1 minus rx equals log square, just wanted to ask or comment, there was a recent book about this kind of difference equation. Maybe you have seen it. I forgot the authors, but if you Google Webster-Krall, the keywords are Webster-Krall theorem, so Webster-Krall something, which is a generalization of Bohr-Molerab theorem for gamma. So they consider in the maximum general, maybe not maximum, but to the big generality, this kind of difference equations with different right-hand sides. Maybe it's not useful in your context. I don't know. Just wanted to mention.
That's interesting to know. So Webster-Krall.
Krall, K-R-U-L-L. Webster-Krall. Webster-Krall theorem, and then there's some recent book on Webster-Krall, blah blah blah. Well, if you mail me, I'll find it precise. I can send you the book just if you email me.
That will be great. Thank you.
And thank you for the great talk, by the way. Thank you.
Are there any other questions? If not, it just remains for me to thank Atul for his very clear and instructive lecture. That ends this particular session now.